Hello, Dan here from howtomechatronics.com, and in this video we will learn how to make a linear servo actuator. Unlike regular linear actuators that move in a particular direction when a voltage is applied, this custom-built linear servo actuator provides precise and repeatable movements that can be easily controlled. It's called a servo actuator because it features a feedback loop system through which we can control the actuator output motion accurately. The input for controlling this linear servo actuator can be either analog or digital. In the case of an analog input, it can be any type of potentiometer like shown here. A linear potentiometer or a common rotary potentiometer, or for example a joystick, which is again a rotary potentiometer, and so on. In case of a digital input, we can control the actuator with an RC transmitter. Of course, for this setup we also need an RC receiver, which goes as an input to the actuator. For both these analog and digital input modes, we only need 3 wires to make a connection, 2 of which are for powering the input device and the third one is for the input signal. A cool feature this custom-built linear servo actuator has is that we can set a custom start and end position for the output rod, as well as adjust the sensitivity or how quickly the actuator will respond to our input. Though my favorite feature is the ability to control this actuator from a PC or a laptop through a serial port communication. We can enter values in millimeters through the Arduino IDE serial monitor and the actuator will move to that position. What's even cooler, we can make a repeatable movements or store the positions by typing save on the serial monitor at each position we want, and then tell the actuator to repeat the movements in a loop by typing run on the serial monitor. Now let me explain everything you need to know about this custom-built linear servo actuator, how it works and how I designed it, so you can also build one on your own. So, the closed-loop control system is based on the AS5600 magnetic rotary position sensor and the implemented PID control for driving the DC motor. Actually, I am using the same custom servo motor controller board that I made in my previous video, which includes its own microcontroller and everything else to easily turn any DC motor into a standalone servo motor. You can check that video out for a detailed explanation of how a servo motor and a closed-loop control system works. Real quick, a servo motor is a closed-loop control system where the input signal or the desired position is compared to the actual position of the motor that we get from the position feedback sensor. The difference that occurs, which is called the error, is then processed in the controller, which commands the motor to move until it reaches that desired position. So this linear servo actuator has the same working principle as a servo motor, but with one additional step of converting the rotational motion of the motor into a linear motion with the help of a lead screw mechanism. Here's the 3D model of this linear servo actuator from where we can see how everything works. The AS5600 magnetic rotary position sensor is located at the backside of the actuator and it keeps track of the rotation of the lead screw. The lead screw that I use has 8mm pitch, which means with each full rotation, the lead screw nut makes 8mm linear motion. The AS5600 is a 12-bit encoder, which means it can output 4096 positions per turn. If we divide 8 by 4096, we get a resolution of 0.001953mm. That's the smallest change in position that the AS5600 encoder can detect. The DC motor that I use is 12 volts motor with included reduction gearbox which outputs 480 RPM. If we divide 480 by 60, we get a value of 8 revolutions per second, and if we multiply that number by 8, because the lead screw has 8mm pitch, we get a linear speed of 46mm per second of the actuator. I found that to be on spot because the maximum travel of this actuator rod is 150mm, so it would take around 2.5 seconds from start to end position at maximum speed, or around 3 seconds if we include the acceleration and deceleration. Therefore, here I used 1:1 gear set ratio for driving the lead screw. The design of this whole linear actuator is based on the size of the custom-built servo motor controller PCB, and the lead screw and the lead screw nut, of course. The PCB had a dimension of 40 by 40 mm, so that was the minimum size of the cylinder block. The 8 mm lead screw nut had outer dimension of 22 mm, so according to it I designed the rod. The nut and the rod are connected with 4 M3 bolts and threaded inserts. At the top of the rod there is a bearing that slides on the cylinder block, and it's used for guiding the rod and preventing it from rotating. At the output cylinder cap we have 4 small bearings which guide the rod out of the cylinder block. Overall, I think the linear actuator came out compact enough considering all the components used. I also managed to fit a micro limit switch inside the cylinder block, which will be used for homing and setting the start position of the actuator. At this point I would like to thank Onshape for sponsoring this video by providing me with this CAD system that I used for designing this custom-built linear servo actuator. Onshape is a cloud-native CAD plus PDM system used by businesses, and there is also a free version for at-home use. Believe it or not, Onshape was actually created by the founders of SolidWorks. With the rise of cloud computing, the SolidWorks founders realized that creating a CAD system from scratch in the cloud could create many new benefits that existing SolidWorks users can't experience. One benefit, for example, is that in Onshape, users are able to collaborate in real time, similar to how Google Docs work, which allows engineering and design teams to be more productive than ever. And you also no longer need to be concerned with who has the most recent version of a file, or checking a file in and out of an expensive and hard to manage PDM system. Onshape also works in a browser, which means it works across all operating system and devices, including iOS and Android devices. Personally, this is one of my favorite features, as I am able to work on my designs at any time at any place. So whether your company uses SolidWorks already and you are looking to modernize your engineering and design, or if you just want to try it out for at-home use, you can create a free Onshape account at onshape.pro/howtomechatronics. You can find the link in the description of the video. Once again, thanks Onshape for sponsoring educational content like this. Back to topic, you can view and explore the 3D model of this custom-built linear servo actuator directly on your web browser with Onshape. The link to it is in the video description. Of course, you can also download the 3D model as well as the STL files needed for 3D printing this project on the website article. The link to it is also in the description of the video. One more thing to mention here is that you can easily increase the maximum travel length of this linear actuator by simply increasing the length of the cylinder block and the rod. I chose these dimensions because I wanted all the parts to fit on a 3D printer with smaller print bed of 220 by 220 mm. The biggest part here is the rod, which is 215 mm long. My new Creality Ender-3 V3 SE did a great job of printing it in a horizontal orientation along the y-axis. Although we need to do a little bit of sanding, printing the rod in this orientation will contribute to smoother operation and stronger rods. When 3D printing, it's important to use the horizontal expansion feature in your slicing software in order to compensate for the expansion of the filament and get more dimensionally accurate parts. I used a value of -0.1 mm, but you should do some test prints to see what values will give you the best results on your 3D printer. I printed the cylinder block along the Z-axis to avoid printing a lot of support material. The Creality Ender-3 V3 SE also did a great job for this print. I was actually pleasantly surprised by the print quality this 3D printer offers considering its price point. It's super easy to set up the 3D printer, it has auto bed leveling, direct extruder, great print quality and increased printing speeds of up to 250 mm per second. All of this for just under $200 makes it one of the best 3D printers for those who are on a budget. You can check out this 3D printer on the Creality store. The links are in the description and the comments of the video. You can also check my detailed review on it on the website. Anyway, here are all 3D printed parts, so now we can start with assembling the linear actuator. First, we need to install the lead screw in place in the cylinder base block. For that purpose, we need to insert this 3D printed nut, which has the same thread as the lead screw. It's a bit hard to screw the nut onto the lead screw as it's a tight fit, but that's what we need here. This nut holds the entire force when the rod is pushing, so the tighter the fit, the more force we'll be able to hold. In addition to that, the nut also has a hole for inserting a threaded insert for securing it to the shaft with a grab screw. The lead screw is held in place in the cylinder base block with the help of two bearings with 22 mm outer diameter. At the back side goes the gear that drives the lead screw. This gear also has a matching thread and two holes for threaded inserts for securing it to the lead screw with grab screws. This connection is also critical as it transfers the entire torque of the motor to the lead screw, so it must not slip. To make this sub-assembly, first we need to install the threaded inserts in place on the gear and the nut, as well as some on the cylinder block. We screw the gear and the nut in the opposite direction, but not too tight as this adds axial forces to the bearings. Then, using some grab screws, we can secure the nut and the gear to the lead screw. Once secured, we can notice that the lead screw is not yet fixed in place. We need to add this plate to the cylinder block, which will ensure that the bearings will stay in place in the cylinder block. This completes this sub-assembly. The lead screw now stands firmly in place while it can freely rotate. Next, we can prepare the rod. The rod is hollow throughout its entire length to accommodate the lead screw. For connecting the lead screw nut and the rod, first we need to install some threaded inserts. At the top side of the rod, we need to install the guide bearing with 13 mm outer and 6 mm inner diameter. We place the bearing on a 3D printed 6 mm hollow shaft and secure it to the rod with an AIM-3 countersunk screw with 10 mm length. The rod is now ready and we can see how it will slide in the guide rails of the cylinder. Next, we need to attach the cylinder to the cylinder base block. Before we do that though, we should install the micro limit switch in place. First, we need to solder the wires to it at the normally closed connection. The wires should be around 15 cm long. The wires are passed through a hole at the top of the cylinder, and then we can secure the micro limit switch to the cylinder with the help of two M2 bolts with 8 mm length. You will need specifically this micro limit switch in order the guide bearing to trigger it just at the right time without hitting something else. If you can't find the exact limit switch mode, of course you can modify the holes and the mechanism. You can find a complete list of all components needed for this project on the website article. In order to attach the cylinder to the base block, we need to install some threaded inserts here. Then we can secure it in place using two M4 bolts with 25 mm length. We should insert just the upper two bolts at this time. The lower two will go a bit later when installing the gearbox and PCB cover, because the same holes are used for securing the cover. Next, we can screw the rod into the lead screw. The guide bearing should go in between the guide rails of the cylinder. By rotating the gear on the back side, the rod will move backward, all the way until it reaches the micro limit switch. Then we can attach the cylinder cap in place. The cylinder cap will accommodate 4 small bearings with 8 mm outer diameter. The shafts for these bearings can be 3D printed. However, we should be careful when inserting them in place, as the part where these shafts go is quite small and it might easily break. It happened few times to me, so make sure they are easy fit. These bearings will support and guide the rod for smoother operation. The cylinder cap is secured in place with 4 M4 bolts. Okay, so next we can insert the DC motor in place. We secure the DC motor with 6 M3 bolts. Then we can install the gear onto the motor shaft. For securing the gear in place, we use 2 threaded inserts and grab screws. Once the gears are properly paired, we can move on with attaching the gears and PCB cover at the back side of the linear actuator. For that purpose, first we need to install a few more threaded inserts into the cylinder base block. Then we can connect the wires to the DC motor. In my case, I directly solder them to the PCB. The length of the wires should be around 20 centimeters. There is a hole in the cylinder base block through which we should pass the wires of both the DC motor and the limit switch. Then we should also pass them through two holders on the cover, which will make sure they stay away from the gear. At this point we can secure the cover to the base block. For that purpose, first we need to insert the two M4 bolts at the bottom side, but not all the way in. We should leave around 2 or 3 millimeters, so that we can place the cover holder in between, and then fasten these bolts together with the cover. This whole operation is a bit messy, but it had to be like that because I wanted the cover to be as small as possible and a single print, and the PCB holders were also blocking the way of the bolts. Anyway, once we are done with the cover, we can install the custom servo motor controller board in place. Like I said, it's the same controller from my previous video where I showed you how you can turn any DC motor into a servo motor. The main component here is the AS5600 magnetic rotary position encoder, which keeps track of the angular position of the magnet attached at the output shaft. In this case, we will attach the magnet to the output gear on the lead screw. The magnet gets perfectly aligned with the AS5600 sensor when the PCB goes in place. For securing the PCB, first we need to insert M2 nuts in the holder's slots and then tighten the PCB with 4 M2 bolts. What's left to do now is to connect the wires in place. The DC motor wires go to the motor terminal block and the polarity should be checked additionally to match with the controller program. Actually, before connecting the motor to the PCB, we can apply some voltage to it to check whether the lead screw mechanism works properly. As for the limit switch wires, as I don't have dedicated pins for this purpose on the PCB, I soldered the ground wire to the ground pad on the electrolytic capacitor and a normally closed connection wire to the clock pin, which is digital pin number 13 on the Atmega 328 microcontroller. The terminal block for the power is right next to the side of the cover, so there is a hole through which I connected a 5.5 power connector. I also added a heatsink to the DC motor driver. Finally, we can put the snap fit lid on the back side and that's it, we are done with this project. Now we can connect any type of potentiometer or an RC receiver to the appropriate input pins and we can control the position of the linear actuator with it. As I already mentioned, in my previous video I explained in details how this controller works, its circuit schematic and how I made the PCB, so you should check that video out if you want to make this controller. Real quick, the main component is the AS5600 magnetic sensor which keeps track of the position of the actuator output. The sensor data goes into the brain of this servo controller board, the Atmega 328 microcontroller, which does the math and then tells the DRV8871 DC driver motor how to drive the DC motor. The DRV8871 DC motor driver can handle up to 3.6 amps of peak current. For powering the board we can use 12 volts, which is then dropped to 5 volts with an AMS 1117 voltage regulator for the Atmega 328 and the other 5 volts components. There is a 2-channel dip switch through which we select the input mode of the actuator, either analog or digital, or via the serial port communication. One of the trimmer potentiometers is used for adjusting the sensitivity of the actuator, and the SMD push button is used for setting the start and end positions. I ordered this PCB from PCBWay. Here we can simply upload the Gerber file, choose the properties of our PCB and order it at a reasonable price. I designed the PCB to have 4 layers, the middle ones are for ground, which increases the price a bit. You can find and download the Gerber file for this PCB on the website article or from the PCBWay project sharing community, through which you can also directly order the PCB. Anyway, you can also make this linear actuator project even without this custom built servo controller. You can use the AS5600 sensor on a breakout board in combination with an Arduino board for controlling the DC motor. Okay, let's take a quick look at the Arduino code now, and on the website article you will be able to find more details of how it works as well as download it. So we start the loop by reading the encoder value or the current position of the actuator and convert it into millimeters. Then, if we are in the serial communication mode, we read the incoming data that we enter on the serial monitor. If the input is safe, we store the current position actuator, or if it's clear, we clear the already stored positions. If the input is integer number from 0 to 150, we use that value as a set point. We enter values in millimeters, but for keeping track of the rotating shaft, we are using degrees, so therefore we convert the millimeters values into degrees values by multiplying by 45. That's so because for 1 mm linear movement, the lead screw should rotate 45 degrees. In case you have a different pitch on your lead screw, this number should be different. If we type run with the help of some while and for loops, the program will run through the stored position repeatedly. On the other hand, if we are in the potentiometer and RC receiver control mode, we check whether we have analog or digital input. If analog, we read the analog input from the potentiometer and use that value as a set point or desired position for the actuator to go to. Similarly, if the input is digital, we read the incoming data from the RC receiver and use that value as a set point. Then we call the read encoder and run motor custom functions to read the current position of the actuator and execute the PID control. With the read encoder function, we read the current value of the sensor in angle values, and with these if statements we keep track in which quadrant the current position of the shaft is. With this information we keep track of how the shaft rotates and when it will make full turn. The total angle is the input value of the PID controller. Using the analog input from the trimmer potentiometer, we can adjust the proportional gain of the PID controller. And finally, we run the PID process to get the output value. We use the output value for driving the DC motors with PWM signal, left or right, or in still position depending on the output value from the PID controller, or the error between the desired and the actual position the encoder reads. The three terms of the PID controller, the proportional, integral and derivative, are defined at the top, and by adjusting them we can get various output responses. The quality, how well the actuator will work and respond to our inputs directly depend on these values. Here I am testing how well this actuator performs. When going back and forth, it gets back in place decently. Here I am moving the rod 1 mm at a time. The first movement was like 0.8 mm instead of 1 mm, but the next 4 were close enough to 1 mm. Here I'm making 4 mm movement and they were about 0.15 mm off. We should notice that the rod has a backlash of around 0.25 mm. This backlash is between the lead screw and the lead screw nut. In addition to that, we have some backlash in the 3D printed gears as well as in the gears of the DC motor itself. If we apply a force to the rod and test the accuracy now, of course we will get even greater error, but this can be improved as well by tweaking the PID controller. However, you will find more details about this on the website article. That would be all for this video. I hope you enjoyed it and learned something new. Don't forget to subscribe, and for more tutorials and projects, visit howtomechatronics.com.